We are EFLATUN UAV team, founded in 2022 at Middle East Technical University, which focuses on advancing UAV technology through research and innovation.
This is our developer team, comprised of 12 members hailing from 5 distinct academic majors and spanning across 5 different academic grades. This is our 8-member competition team that will manage and execute the competition process. We have crafted Betelgeuse 2 and its subsystems for the mission. It will run autonomously, managed by just 2 operators, a safety pilot and a ground control station operator. In accordance with SUAS competition regulations, teams are allotted 15 minutes for UAC setup. To ensure compliance, we have opted for a modular design comprising 5 key components, allowing us to complete our UAC setup within 20 minutes. The mission parameters stipulate a maximum distance of 15 miles with teams allotted a duration of 30 minutes. Consequently, our UAV has been engineered with the capability to cruise a speed of 30.02 miles per hour, ensuring timely completion of the mission with a safe battery margin. The UAV is required to conduct flight operations and payload drops with safety and stability. To accomplish this, the system parameters have been tuned to ensure optimal performance and adherence to safety protocols. Our UAV is engineered to adhere to SUAS regulations, which stipulate a maximum runway of 600 feet for HTOL operations. So, we have designed it to achieve a shortened takeoff capability requiring just 250 feet of runway space. To facilitate the carriage and release of 5 payloads, our UAV has been engineered with a robust payload capacity. The system must accurately identify airdrop locations for diverse payloads. To achieve this, it employs a segmented design capable of detecting objects' shape, color, and letter. Additionally, the system is tasked with avoiding other UAVs. To achieve this, we've developed an AI model trained to detect and steer clear of them. A meticulously designed fixed-wing UAV is configured to execute the entire mission. It features a specialized drop mechanism for payload delivery and is equipped with autopilot, GPS, telemetry, and lidar modules for autonomous operation. Additionally, an advanced imaging system with a gimbal camera captures high-quality images for ODLC, processed on board using an integrated computer. After passing pre-flight checklist, the UAV is powered, payloads are secured, and the mission begins under the supervision of a ground control system operator and a safety pilot. The UAV takes off, autonomously follows predetermined waypoints, conducts ODLC at the drop area, delivers payloads, and returns for a safe landing. The decision to employ a fixed-wing configuration to Betelgeuse 2 was deliberate, owing to its advantages in speed, lightweight, maneuverability, extended endurance, and payload capacity. With attention to optimal dimensions and weight distribution, this configuration ensures the timely delivery of payloads to the designated mission area. And these tables show that all electronic components under distribution in Betelgeuse 2. In Betelgeuse 2, a fixed-wing configuration with twin brushless electric motors on a high-wing design is used. A V-tail configuration is added to the tail section to reduce drag forces. Aerodynamic optimization included establishing parameters such as a thickness ratio of no more than 10%, manufacturability, low camber, low drag, and low momentum. Analysis of over 300 airfoils using XFLR5 program was followed by analysis on the top 5 options using NSS. Furthermore, control surface area calculated to fulfill the demand of high maneuverability, stability, and high payload capacity. This rigorous process yielded the values presented in the table. After completing the wing and tail design, focus shifted to the fuselage. A fuselage design with a slightly low drag coefficient, capable of generating lift and maintaining clean airflow to the tail using the downwash effect was developed. The final fuselage dimensions are 187 cm in length, 25 cm in width, and 18 cm in height. After completing the fuselage design, the conceptual design process was finalized. Detailed aerodynamic analysis of the integrated wings, fuselage, and tails followed, recalculating lift and drag forces at both cruising and maximum speeds. These analyses provided essential values such as weight, center of gravity, and required thrust for the aircraft's detailed design. Motor and propeller selection was based on the required thrust value, ensuring a thrust-to-weight ratio greater than 1. T-Motor 80 for the 120s 560 kV motors paired with 16 to 8-inch propellers for 6S batteries were chosen. Thrusters achieved 7 kg of thrust at 90% throttle. These motors were positioned in a tractor configuration on the wings. After these stages, detailed aircraft design began, emphasizing lightweight construction using composite materials. Carbon tubes and ribs from carbon fiber sheets were used for the wing and tail frames, while wooden plates instead of carbon fiber were chosen for the fuselage frame due to the electrical conductivity concerns. Sandwich panels comprising PVC foam between layers of carbon fiber were preferred for the outer surfaces for the fuselage, wings, and tail due to their lightweight and rigid structures. After completing the initial stages of surface and chassis design, electronic components were placed in such a way that the center of gravity remains ahead of the center of lift. The position of the center of gravity was located 137.4 mm behind the leading edge of the wing. Following the stages, structural analysis were conducted on the wing frames using the shrinkage method with applied loads, and it was calculated that the wings would deflect by 80 mm under a 2G load. The landing gear heights were calculated to provide sufficient clearance, taking into account the body height and propeller diameter with a climb angle of 6 degrees during takeoff. Additionally, the positioning and widths were calculated using a formula dependent on the desired turning radius on the ground and wingspan, resulting in the values obtained in the graph. After completing the detailed design process, we moved on to the production phase. We designed MDF molds to produce carbon fiber surfaces and machined them on a 5-axis CNC machine. Once the molds were ready, they were prepared for the molding process. Vacuum bagging method was employed during the molding stage and left to cure for a day. After curing, the surfaces were trimmed. After this stage, we began manufacturing the wing, tail, and fuselage frames. We cut carbon fiber and wooden plates using laser cutting for these components as well. The assembly of these frames were also done within the molds. After these stages, we integrated the surface with the frames and proceeded to assemble all aircraft by placing the electronic components in their designing positions. After completing the production, we verified the design and analysis of our aircraft through 4G, minimum turning diameter 45 meters.
Our payload system consists of 3 parts. The parachute, 6 meters per second is assumed and the area calculated as 0.27 meters square. Lots of tests were conducted to ensure the configuration. Results demonstrated in the accompanying videos. The airdrop lands safely using the parachute. The release mechanism facilitates the release of payload from the UAV. The payload securely fixed onto a linear shaft at the correct angle moves along it via a linear bearing. The bearing is controlled by a servo arm. When the servo arm rotates to a specific angle, it releases the bearing, allowing the payload to slide down in a controlled manner. The mechanism is designed to ensure reliable payload deployment during missions. The covers designed to enclose the parachute are equipped with the springs that provide tension to keep them open. The servo arm is responsible for holding the covers in place in a closed position. When the servo arm is activated and rotates, it releases its grip on the covers. The stored energy in the springs causes them to rapidly open. This opening action creates an opening for the parachute to deploy. The parachute is free to deploy and slow the descent of the payload.
For the obstacle avoidance task, we developed a high-level algorithm that captures real-time stream from camera, tries to detect other UAVs with the AI model, and if detected, implements special measures to escape those aerial vehicles. The AI model is a YOLO V8 large object detection model trained on the custom dataset gathered by our team. The dataset consists of more than 7,000 UAV images in different visa conditions. When Betelgeuse 2 is outside of the ODLC mission area, the camera will rotate towards the direction of motion and run the model to detect the UAVs on the front. For escaping from other UAVs, the model will extract certain features and decide on whether the other vehicle is approaching Betelgeuse 2. If so, the Betelgeuse 2 will roll slightly left or right, opposite of other vehicle's direction. Our team carried out several tests using the trained AI model and flying 2 and more UAVs at the same time. As a result, 92% accuracy result was recorded. Betelgeuse 2 was also successful in implementing escape maneuvers from other UAVs. For the imaging and ODLC system, we looked for a quality camera to capture small objects in real time. Among available cameras, we decided to use CE-A8 Mini due to its high resolution, lightness, zoom feature and built-in gimbal. CE-A8 Mini has 21mm focal length, effective resolution and image sensor able to record small objects from altitude with high quality. The high-level ODLC algorithm consists of several stages, which are real-time video capture, object detection, classification of standard objects based on 4 criteria, and localization calculations, after which airdrop decision is made. For the detection part, we used YOLO V8 large detection model and trained it using our own dataset of mannequins with assigned class 0 and different letter and shape combinations class 1 on different backgrounds. As a result, our team had more than 20,000 annotated images per class. We trained detection model over 170 epochs using batch size of 1 and learning rate of 1000. Additionally, the model was accelerated using NVIDIA TensorRT to achieve optimal frame rate. Before deciding on YOLO V8, we also tested other models such as RCNN and YOLO V5 on Coca dataset, and eventually YOLO V8 showed the best performance in terms of mean average precision and speed. In the classification stage, we developed YOLO V8 medium classification models. For this, we ran detection model on videos and saved detected crops that were divided into subclasses for shape, letter, shape color and letter color models. As a result, over 5,000 crops were obtained per subclass. The YOLO classification model was chosen over other image processing methods due to high precision and speed. For localization, we employ a georeferencing formula to calculate the coordinates of the object center on the ground. This involves utilizing the initial x and y coordinates as well as the width and height parameters of the bounding post. The resulting coordinates are then transmitted to the autopilot system using Mavros for airdrop.
The communication system of the EFLATUN UAV team ensures a seamless interaction between 3 key points: the aircraft, ground control station and remote pilot. This tripartite communication network consists of control, telemetry and Wi-Fi modules. On the screen, you can see all connections of communication system, which we are analyzing as 3 different communication methods in 3 subsystems. Pixhawk serves as the central control unit for the Betelgeuse 2S UAS. Integrating with onboard sensors like GPS, airspeed and LiDAR, these sensors provide essential data. We use RFD900X modules operating at 915 MHz frequency to comply with FCC standards. These modules track flight data and enable us to make safety corrections. During ground tests, we found no signal issues up to 2 miles. Additionally, RFD900X offers advanced features like encryption and frequency hopping spread spectrum for enhanced communication and reliability. The role of the mission control system in communication is related to transmitting video feed and mission data using Ubiquiti Wi-Fi module. The necessary system for this purpose consists of 4 electronic components visible in figures. The Wi-Fi module is essential for seamless real-time communication between the ground control station and the UAS. It enables high-speed data transmission for video streaming, telemetry data exchange and command transmission, functioning reliably over short to medium ranges. The GCS includes the mission planner for comms with aircraft via telemetry, the RC for manual control, and the Wi-Fi modules for the video feed transmission. Telemetry ensures efficient communication and control pre-flight and real-time command transmission between the mission planner and Pixel Cube Orange Plus during operations, allowing operators to control the aircraft's flight paths, behavior, and parameters. We use a long-range RC module pair to establish a connection between the remote controller and the UAV. This keeps the signal strong even over long distances and in challenging environments. It helps us control the UAV's flight paths precisely and making everything safer and smoother. Our Wi-Fi modules, enhanced with sector antennas, establish a strong link between the ground station and UAV for reliable transmission of real-time video and telemetry data. This ensures uninterrupted connectivity and constant control for operators throughout the flight. Our team extensively tested communication performance, assessing range and reliability at various distances and environments. As a consequence, rain degrades connections, while interference-free areas strengthen them. Data transmission works reliably at shorter distances. Independent tests showed stable RFD900X connections up to 2 miles. And FRSky's R9M and R9SX pair maintained reliable connections up to 3 miles. Autopilot system of the team, Pixhawk Cube Orange Plus was selected as the flight controller due to its reliability, accuracy, proven performance, and advanced features. Pixhawk, an adaptable autopilot system for autonomous vehicles, features a robust microcontroller and a suite of sensors. Ensuring stable flight control, it supports PX4 and autopilot software, offering autonomous flight modes and mission planning tools. The Pixhawk's internal sensors, including accelerometers, gyroscopes, compass, and barometer, track the aircraft's motion, direction, and altitude, ensures a stable flight. GPS provides accurate location data, aiding precise navigation. LiDAR measures distances by emitting laser pulses, detecting obstacles with precision, and airspeed sensor monitors airflow speed, optimizing flight performance and safety. These sensors, integrated into the Pixhawk, enhance navigation, obstacle avoidance, and flight control capabilities of our unmanned aerial vehicle. The Pixhawk Autopilot, enabling the UAS to navigate predefined paths, execute maneuvers, and accomplish missions without human intervention. The UAS spent 90% of its flight time in autonomous mode, showing the autopilot's strong autonomous flight capabilities. Across 25 waypoints, the team achieved an average waypoint miss error of 0.5 meters, showcasing the autopilot's precision. Pixhawk's autopilot system has proven to be a reliable and effective platform. We are pretty happy with Betelgeuse's system at the moment, but we have also considered a few other approaches in getting to this point. Although these have been dropped during our various reviews, we have got some ideas that we are considered but ultimately rejected. We initially thought about the quadcopter and VTOL fixed-wing UAS. However, when we look at them separately, in terms of efficiency, durability, load capacity, and speed, we decided that the best choice was HTOL fixed-wing UAS. Prioritizing the safety of our members over the equipment, ensuring that all operational decisions are in accordance with this principle, foreseeing potential malfunctions proactively by preparing for potential failures. As a team, we have developed a risk plan focusing on electronic software and physical safety. We ensure safe flights by following strict safety measures. Our operations take place within a dedicated school facility, prioritizing everyone's health and safety.
For the UAV full mission test, we recorded the UAV takeoff, airdrop, and landing in one video. Generally, our team completed 18 flights with a total flight time of 397 minutes. Of this time period, 350 minutes were autonomous flight time. During these flights, our team attempted 29 airdrop trials, and of these 29 trials, 23 airdrops were successful, achieving a success rate of 79%. At the same time, our avoidance model had 92% of accuracy and our ODLZ model had 96% of accuracy. Our team has fulfilled all the requirements of the competition and was able to complete the full mission task.
We tested our aircraft against the necessary requirements, including performing a manual takeoff and landing. At the second and third flight, we heavily focused on testing the required tasks.
Betelgeuse 2 is the result of 2-year hard work, dedication, and prolific teamwork. Building Betelgeuse 2 has been an unforgettable adventure and invaluable experience, filled with overcoming different challenges, discovering new opportunities, and meeting amazing people. Wishing best of luck to everyone competing at SUAS 2024 and looking forward to meeting all of you. Thank you for the attention and see you at the SUAS 2024.